Did you know? There's a material made from individual carbon atoms linked together and forming structures with a diameter just 1/10,000th that of a human hair, yet capable of withstanding forces far exceeding steel. That material is the single-walled carbon nanotube. At its core, a single-walled carbon nanotube is a hollow tubular structure formed when a single layer of carbon atoms, arranged in a hexagonal lattice, curls seamlessly like a cylinder. To get these highly reactive carbon atoms to line up neatly into tubes, the key lies in the catalyst, metal organic compounds like iron or cobalt. Currently, 3 mainstream methods exist for producing single-walled carbon nanotubes, each with distinct advantages and disadvantages. The first is chemical vapor deposition, CVD, which relies on high-temperature decomposition of gaseous carbon sources. Carbon atoms dissolve and precipitate onto metal particle surfaces to form nanotubes. This method dominates industrial production, offering the best balance of scale, cost, and controllability. The second is arc discharge, which evaporates carbon materials via electrode discharge to form tubes. The third is laser ablation, where lasers bombard carbon targets to generate nanotubes. Laser ablation yields the highest purity, followed by arc discharge, but both methods are costly and low yield, primarily used for research. Among these, CVD's airborne tube fabrication process is particularly representative. First, inert gases like argon completely evacuate air from the reactor, precisely regulating the furnace temperature to 1,280 degrees Celsius. This temperature maximizes catalyst activity while preventing premature carbon source decomposition and waste. An injection pump precisely delivers carbon sources mixed with ferrocene into the furnace, where precursors instantly decompose into nanoscale catalyst particles. These particles float while absorbing carbon atoms released from decomposing carbon sources. As carbon sources are continuously supplying, carbon layers form on the catalyst surface, naturally curling into tubes. A complete single-walled carbon nanotube thus grows out. Despite its apparent simplicity, the process demands precise control, excessive temperature. Catalyst particles agglomerate and grow larger, resulting in carbon tubes with uneven diameters and significantly reduced performance. Overly rapid supply. Excessive feeding of carbon source and catalyst produces large amounts of impurity carbon, drastically lowering tube purity. Gas ratio imbalance. Deviations in reaction gas ratios directly halt carbon tube growth. Through precise control of temperature, catalyst feed rate, and gas ratios, researchers now produce high-quality carbon nanotubes exceeding 30 centimeters in length with over 96% purity. Space elevator cables, integrated circuits, fiber materials. These revolutionary applications may soon become reality. What changes do you think they'll bring to our daily lives first?